Hello everyone, my name is Mohamed ElMenshawy and I'm glad that our paper is accepted in ISARC conference. The title of our paper is Exploring the Potential of Reinforcement Learning in Pipe Spool Scheduling in Industrial Projects, and it is co-authored by myself, Dr. Lingzi, Brian, and Dr. AbouRizk. Industrial projects include various facilities such as petrochemical plant, power plant, and oil and gas facilities. Piping is considered a main component in these projects due to its critical role in transporting fluids and gases throughout the facility. The piping systems must accommodate the project specifications, conditions, and operational demands. The complexity of these systems includes a variety of materials, sizes, and configurations, each tailored to specific functions within the project. So the large and complex pipes you see in these projects are often fabricated off-site in a fabrication shop, and they are divided into several assemblies called pipe spools. You can see a pipe spool in the right photo. These spools are made of several components and fittings. You can see some of them in the left photo. So for scheduling the fabrication of these pipe spools in a shop, based on the available fitting station, processing time, and due date, the spool is assigned to a station to undergo fitting. Once the spool is fitted, the welding station, processing time are checked, and then a spool is assigned to a welding station. Finally, inspectors can check the spools. This scheduling process is conducted manually in the fabrication shop. So our objective is to try to explore the automation of this scheduling process by developing a reinforcement learning model. So we checked the previous efforts to understand the current status. There are some studies which use simulation approaches to simulate the fabrication process. These studies helped in understanding the process by studying the fabrication time, identifying bottlenecks, measuring resource utilization, but it did not address the scheduling process. Another set of studies in job shop scheduling used meta-heuristics such as genetic algorithms, but they were not applied on large scale and real-world scenarios. And they also have some limitations when it comes to a dynamic and changing environment. Then the last set of studies applied reinforcement learning in the manufacturing domain to solve the job shop scheduling, but they were not scalable to a real-world scenario, and they focus on the manufacturing setting, which differs from the construction industry, as the manufacturing industry is considered a closed and monitored environment. So in this research, we explored reinforcement learning applications and how it can be used to automate the scheduling process of pipe spools in a fabrication shop. So let's start with an overview about reinforcement learning. It is a type of machine learning where an agent takes an action, and once an action is taken, there is a feedback from the environment in the form of rewards or penalties based on these actions. The agent has one goal in mind, which is to maximize the total rewards. The reinforcement learning model includes 5 main components. The first one is the agent. It takes actions and affects the environment. Then the action. These are the set of choices that the agent can choose from. Then we have the environment. It represents the medium where the agent takes an action, and in our case, it is the fabrication shop. We have the states, or sometimes referred to as observations, and we can say that these are the conditions of the fabrication shop that we are keeping track of. And finally, we have the reward, which is the feedback after an agent takes an action. There are 2 types of reinforcement learning. The first one is called model-based RL, where there is a need to develop a transition model for the environment. And it means that this transition model shows the percentage of moving from one state to another in the environment. This type is complex, as it's almost impossible to design a transition model for a dynamic and changing environment. On the other hand, the second type is called model-free type, and this one does not require building this transition model, and the agent learns directly from the interaction with the environment. And this is the type we used. Now let's go through a main concept in reinforcement learning, which is the Q value. So now let's assume that you are in a specific state in the environment. The agent takes an action and gets rewards. Then it moves to the next state. It takes another action. It receives a reward. So the Q value is the cumulative rewards for all the actions. And this is a core concept in reinforcement learning. So in our model, we started with preparing a data set that mimics the pipe spool fabrication shop with information like start date, fitting processing time, resources required for each spool, and the due date for each spool. Then we define the actions that could be taken by an agent. The first action is first come, first serve, which prioritizes the components that first arrived in the shop. And the second action is shortest processing time, which prioritizes the spools that have the shortest processing time. Then we have the states that we are monitoring, and they are the average processing time, average slack, and average resources per spool. Finally, we have the reward function, and here we decided to focus on the number of spools that were fabricated within or after the due date. So our reward is either 0 or -1. 0 in case the spool is fabricated before or by the due date, and -1 in case the spool is finalized after the due date. So our data set included approximately 1,800 records of pipe spools, and we used the Dueling Deep Q network, DQN algorithm, to estimate the rewards. And we developed the model using Python libraries such as PyTorch, OpenAI Gym, Pandas, and Matplotlib. And we conducted the first experiment using these hyperparameters, which are 100 episodes, 0.0025 learning rate, 32 mini batch size, 0.9 for epsilon, and 0.9 for discount rate. So these are the results of our model. We performed 2 more experiments with different hyperparameters to see the impact on the model. Experiment 2 shows a relatively improved result, as the lowest average reward reached approximately -50 when compared to the first experiment, where the lowest average reward reached approximately -70. And in experiment 3, we can see that the lowest average reward reached approximately -140, which is the lowest among the 3 experiments. So throughout this research, we developed a reinforcement learning model that can handle the scheduling process, and we believe that it has the potential to outperform the dispatching rules. This research is considered the first to explore reinforcement learning application in scheduling industrial projects. Since it's considered the initial step in reinforcement learning, we have some limitations that we would like to address in the future work, such as widening the scope of the model to include other processes and not the fitting process only, and also to include more dispatching rules in the action set so it can be chosen by the agent, and finally train the model on a real-world case study. We would like to highlight that this research is supported by the Collaborative Research and Development Grant, and we would also like to thank our industry partners, PCL, for their continuous support throughout this research. Thank you so much for listening.